Let's have a look at finite state automata, or FSA for short. In this series of videos, we're going to look at how FSA are useful, use them in an example to test for valid sentences, and then build our own automata to explore other uses. So, what do these words mean? Finite state automata. Finite means that there are a limited number, as opposed to infinite, which means the number is unlimited. A state is a condition at a particular time, and automata is the plural for automaton, a machine that functions on its own, following some simple instructions and rules. Therefore, a finite state automaton is a simple machine with a finite number of states. If you have any experience with text-based programming, calculations in Excel, or even writing sentences in Word, you may have encountered the dreaded syntax error, where you accidentally left out a bracket or misspelled a word. Even before your computer runs your code or makes that calculation, it knows that you've made a mistake, and it can often tell you exactly where it is. We can use finite state automata to find some of these errors. Let's take a look at this simple automaton I made. Its purpose is to check that a given sentence starts with a capital letter and ends with a full stop. It may seem a little daunting right now, so let's look through it step by step. First, we can see that this diagram has 4 circles, labelled 1, 2, 3, and 4. These are the different states of our automaton. Between these states are arrows labelled with U for uppercase characters, S for a full stop, and L for lowercase characters, as well as any other punctuation. These represent transitions from one state to the next. For example, if we are at state 1, then the U arrow will transition us or move us to state 3, while the LS arrow would transition us to state 2. Here LS just means that both L and S result in the same transition. Now note that the arrow on the far left is not labelled and does not transition between states, instead only entering state 1. This tells us that state 1 is the start state. So, whenever we run through this automaton, we always start from here. Lastly, state 4 on the right is 2 circles, telling us that this is an accepting state. For this example, acceptable sentences that begin with the capital letter and end with a full stop will result in transitions that end at this state. We can have any number of accepting states. Even the start state can be an accepting one, but we can only have one start state. Let's get a fresh diagram, exactly the same as before. How do we actually use it? Let's say we get the sentence moo. We can already see that it starts with a capital letter and ends with a full stop, but let's run it through the automaton to see what happens. Beginning from the start state, which is 1, we take each character in turn, following the transition for each one. The first character, M, is uppercase, so we follow the U transition to state 3. Then we have a lowercase o, so we follow the L transition, which loops around and back to state 3. Another lowercase o, so again we follow the L transition back to state 3. And lastly we have a full stop, so we follow the S transition to state 4. So we've gone through the string of letters and ended up at state 4. Remember from before that this is an accepting state because it has 2 circles. Since we ended up in an accepting state, the sentence moo is accepted. It does indeed start with a capital letter and end with a full stop. Let's look at another sentence, url.com. Starting again from the start state, we take the uppercase letter U transition to state 3, then an uppercase R transition to state 3, another uppercase L transition to state 3, a full stop transition to state 4, a lowercase c transition back to state 3, another lowercase o transition to state 3, and lastly, the lowercase m transition to state 3. This time we are not at an accepting state, so even though we passed through the accepting state, the automaton does not accept url.com as a valid sentence. However, with the addition of one more full stop, we can make this into a sentence accepted by the automaton. In a more general sense, there are 3 extra words we often use in finite state automata. The first is called the alphabet of our automaton. This is just a list of all possible inputs that result in a transition. In our example, our alphabet is U, S, and L. The sentences we use to test this automaton are known as strings, which are sequences of inputs from our alphabet. Mu and url.com are examples of this. Lastly, we have a language. This is all the possible strings that are accepted by our automaton. Mu is one of the many strings in this language, but although url.com is a string, it is not in our language because it was not accepted by our automata. By now we should have an okay understanding of finite state automata, what they're used for, and how to read them. Let's try to create our own. First up, we need to define what we want this automaton to achieve. Let's go with this. This automaton is to accept any string of A's and B's that has no more than 2 B's in a row. Okay, we have our definition. Now let's break it up to understand what it means. Any string of A's and B's. This tells us that in our alphabet we have 2 transition types, A and B. Accept no more than 2 B's in a row. This tells us that our language, or the set of strings our automaton will accept, is all strings with at most 0, 1, or 2 B's in a row. So let's begin our diagram. A good starting point is the start state, a circle with an arrow into it. Let's call this state 0. That's great. What else can we do? Well, let's look at what we expect to happen if we give the automaton nothing. A string containing 0 A's and 0 B's. That may seem a bit odd, but an empty string, denoted as epsilon or sometimes lambda, is very useful for understanding how our automaton works. So, we put in nothing. There are at most 0 B's in a row in our string. 0 B's is obviously fewer than 3 B's, so the string is accepted. This means that our first state is also an accepting state. Let's give it another circle to show this. Now we can look at what happens when we transition away from our start state. What conditions will result in a string that is not accepted by our automaton? From our definition, that would be a string that contains 3 or more B's in a row. Therefore, we need to add more states. One for 1 B in a row, named 1. One for 2 B's in a row, named 2. And one for 3 or more B's in a row, named 3. We can connect them with B transitions. Each transition represents an increment of the number of B's in a row by 1. What can we interpret from these new states? We know from our definition that if there are 0, 1 or 2 B's in a row, that string so far is still acceptable. Therefore, we can call states 1 and 2 accepting states also. We get to state 3 after 3 B transitions in a row, so this must be our non-accepting state. No matter what character we put in after this, we already know that there have been 3 B's in a row, and so the string is not acceptable. Let's show this by adding a loop transition back to state 3 and calling that A, B. Both A and B follow this transition. State 3 can also be called a trap state, as once we get there, there is no transition out again. The last thing we need to do is show the A transitions out of states 0, 1, and 2. Let's take another step back from our automaton and think about it logically. We have any number of B's in a row, and then we get an A. That breaks our row of B's, and we go back to having 0 B's in a row. Now back to our automaton. We have 0, 1, or 2 B's in a row, and then we get an A. We just decided that we go back to the beginning, so let's do it. Our A transitions are from 0 to 0, 1 to 0, and 2 to 0. So have we finished? Let's check. State 0 has an A transition and a B transition. State 1 has an A transition and a B transition. State 2 has an A transition and a B transition. And State 3 has an A transition and a B transition. We have our start state, 0, and we have our accepting states, 0, 1, and 2. Awesome! All we have to do now is make sure it works. I'll leave you to run through it with a few test cases. If you're watching on YouTube, then leave us a comment. Let us know how you go or if you have any feedback on this series of videos. And for more information and examples, check out the Computer Science Field Guide. Follow the link in the description below and navigate to Chapter 14, Conformal Languages. Thanks for watching.